Welcome back to the Deep Dive. It is Friday, January 30th, 2026. And if you have been anywhere near, well, anywhere at all in the last week, you know what the world is buzzing about.
It is genuinely hard to miss right now. You have to be living under a rock. And even then, the rock probably has a notification about it.
It's absolutely everywhere. Spatial computing is having its big moment. Again.
The cycle has come back around.
Mm-hmm.
We are riding the hype wave. And it feels a little different this time.
It does. We're seeing all the headlines, the unboxing videos, the hot takes on the new Apple Vision Pro 2. Rumors are just swirling about this thing called the Vision Air.
It feels like the consumer tech world is just exploding. Everyone's talking about headsets and pass-through.
And whether or not they look ridiculous wearing them, which, is still a valid question.
It is, but it feels like we've hit that tipping point. The hardware is finally starting to catch up to the sci-fi promises we've been hearing for what, a decade?
Exactly. But, and this is why I love doing these deep dives, we are going to pivot. We're going to acknowledge the shiny new headsets, of course. We have to. They're the Trojan horse that gets us into the real conversation.
They're the catalyst, absolutely. They get everyone in the room.
But the stack of research you've brought in today, it suggests that the real revolution, the one that's actually going to change how the global economy functions, it isn't happening in the living room?
No. Not at all.
Nope.
It's not about watching movies on a giant virtual screen.
It's happening in the factory. It's happening on oil rigs, in automotive plants. It's this whole concept of the phygital continuum.
That's the key word for today, phygital.
Which, I have to be honest with you, is a terrible word. It just is. It sounds like a new kind of energy drink or something.
It's not the most elegant portmanteau, I'll grant you that. But it's sticky. And it actually describes the reality of what's happening perfectly.
We'll see. But our mission today is to look past that consumer hype. We want to understand how immersive tech combined with AI and this thing called Edge IoT is literally rewriting the rules of manufacturing, energy, and even culture and heritage.
I mean, we are talking about some truly mind-bending applications.
We're talking about robots that understand spoken Greek.
They do, fluently. And more importantly, they understand physics, which is the real breakthrough.
And factories that exist entirely in the metaverse before a single brick is laid.
The metafactory. It's a crucial concept for saving money and, frankly, saving people's backs.
And holographic musicians. A drummer in Tokyo playing with a singer in London.
And they don't miss a beat. It's seamless.
So we have a lot to unpack. We've got a report from UC Today that's really focused on the Apple launches, and then we have this massive, and I mean massive, research paper from the Alliance for IoT, AI, and Edge Continuum Innovation, the AIoTI.
It is dense. It's heavy reading, for sure, but it is incredibly rich with data. It maps out the future of industry in a way that very few documents do.
So let's dive in. Segment 1, the hardware catalyst. Because even if the industrial stuff is the main course, Apple is the one setting the table.
They always are. They set the pace for the market. When Apple moves, the entire supply chain moves with them.
So it's early 2026. The Apple Vision Pro 2 has been announced. It's slated for late this year, maybe early next. We've got specs, we've got details. But before we get to the new stuff, we have to address the elephant in the room with the first generation.
A hard reality check.
The $3,499 hard reality check.
Exactly. Look, when the first Vision Pro launched, it was an engineering marvel. Nobody disputed that. The screens, the eye tracking, the build quality, it was science fiction made real.
Oh, it was incredible.
But for businesses, it was such a tough sell. You had IT departments looking at that price tag and just saying, this is an R&D experiment. This isn't a tool we can give to every employee.
Right. It struggled to move beyond that cool demo phase, didn't it?
It really did. It was a very, very expensive paperweight for a lot of companies after the initial excitement wore off.
You show it to the CEO, they say, wow, this is the future, and then it goes right back in its very elegant box.
Precisely. And Apple knows that. They listen to the market, even if they pretend they don't.
Right.
So the Vision Pro 2 isn't just a spec bump. It's a really strategic correction, and it starts with the silicon.
The M5.
The M5.
We're jumping from the M2 in the original all the way to an M5. That sounds like a pretty big leap. For the listener who might just think, oh, faster processor, big deal. Why does this matter so much for business?
It is a massive, massive leap. In the XR World Extended Reality, we talk about the holy trinity of enterprise compatibility.
Okay.
Speed, thermal efficiency, and battery life. You need all three.
And thermal efficiency is the one that always gets me because nobody wants to wear a toaster on their face for 8 hours.
Exactly. That is the fundamental bottleneck. The M2 was powerful, but it generated a lot of heat. And when a chip gets hot, a few things happen, all of them bad for this use case.
It slows down.
It throttles, right? It slows down to protect itself. Or the fans have to spin up, which gets noisy and annoying. Or the device just gets physically uncomfortable to wear.
And if you're, I don't know, training a surgeon or a jet engine mechanic and the device overheats or the battery dies in 45 minutes?
It's useless. It's a toy. You can't run a shift on that. You can't tell the patient on the operating table, hang on, my eyes need to charge.
Right.
So the M5's generational leap is all about performance per watt. It's about delivering that incredible speed without the thermal penalty. It makes the device viable for actual work shifts, not just 20-minute demos.
Then speaking of wearing it for a shift comfort, the report mentions a totally redesigned head strap.
It seems like such a minor thing, doesn't it?
Oh.
The strap. But it's absolutely critical. The number one complaint with the first gen, by far, was neck strain. It was too front heavy.
I remember the reviews. People called it the eye ache.
They did. And you can't transform the workplace if your workers are in physical pain after an hour. It's that simple. If the tool hurts you, you will not use it. It doesn't matter how magical the software is.
So they're fixing the engine with the M5. They're fixing the chassis with the head strap. What about the brain? The AI part of this?
This is where the upgrade to the neural engine comes in. It's a huge focus. In a modern hybrid office or a digital factory, the device has to map the environment instantly. It needs to know where the walls are, where the desks are, where other people are.
And it needs to render those personas, the digital avatars of your coworkers, in real time.
And do it photorealistically, which requires a staggering amount of math, a massive amount of AI crunching power. The Vision Pro 2 is leaning heavily into this new neural engine to make remote collaboration feel less like a cartoon and more like actual presence.
And on the software side, we're looking at visionOS 26. But there was one detail in that UC Today report that really caught me off guard.
I think I know what you're going to say.
PlayStation VR2 controller support.
Yeah, that caught everyone by surprise.
It feels so un-Apple. Apple hates buttons. They want everything to be these elegant, minimalist hand gestures. Just pinch the air.
They do. It's their whole design philosophy. But they've learned a hard lesson from the enterprise market. For precision industrial work, hand gestures are not enough.
They're too vague.
They're too vague, and they can be tiring. If you were controlling a robotic arm that costs $5 million, or you were navigating a complex 3D blueprint of a skyscraper, pitching the air feels imprecise. It's not reliable enough. Sometimes you just need a controller. You need buttons. You need haptics.
That's a huge concession to utility over minimalism. It's Apple admitting that sometimes a tool actually needs a handle.
Exactly what it is. It signals that they're taking the enterprise and prosumer market seriously, not just the watching movies on an airplane market.
But this is where it gets really interesting for the economics of it all. They aren't just launching the Pro 2. The strategy's bigger. They're splitting the product line.
The strategic split. This is the big move. Enter the Vision Air.
The Vision Air. So I assume this is the diet version, the less powerful, cheaper model.
It's the mainstream version. Lighter, for sure.
Yeah.
Materials that aren't quite as exotic and premium, maybe slightly lower resolution screens, a slightly less powerful chip. The best analogy is the iPhone SE versus the iPhone Pro Max.
For a business, that changes the entire calculation.
Completely. If I'm a logistics manager at a huge shipping company, I can't go to my CFO and ask to buy 500 Vision Pros at $3,500 a pop for my warehouse pickers.
You'd get laughed out of the boardroom.
Immediately. The budget just doesn't exist for that.
But
if the Vision Air hits a competitive price point, let's say maybe $1,500, suddenly I can scale. I can actually deploy hundreds of units and see a real return.
so the Pro 2 becomes the high-end executive tool.
Exactly. The Pro 2 is for the medical imaging specialist who needs pixel-perfect resolution. It's for the high-end automotive designer at Brembo who needs flawless color accuracy. The Air is for the workforce. It's the tool for a scalable rollout.
But the report ends with a pretty stark warning, doesn't it? It says the hardware is just the vessel.
And that's the perfect segue to the AI/OTI paper and our main topic today.
Yeah.
Companies are done with dazzling demos. They are completely over the wow factor. They need ROI. They need to see a real impact on productivity.
A headset is only as good as what you can actually do with it.
That's the bottom line. The magic has to translate into money saved or money earned.
Which brings us to the phygital world.
Here we go.
I promise we'd unpack this term. The AIoTI paper calls it the Industrial Real Digital Virtual Continuum.
It's a mouthful, isn't it?
It really is, but the source material really leans into this. It's not just about VR or AR, it's about the seamless blending of physical assets with their digital intelligence.
Think of it this way. For a long, long time, we've talked about the concept of digital twins.
Right, a digital copy of a physical thing. Like, you have a 3D model of a car engine on your computer screen, and it shows you the real-time temperature from a sensor on the actual engine.
Correct. That's a digital twin. But this new research introduces a more advanced, more powerful concept, the immersive triplet.
The immersive triplet. Okay, break that down for me because twin makes perfect sense. There are two. What's the third element?
So element one is the physical asset, the real thing, the robot arm on the factory floor, the wind turbine in the North Sea, the historical building in Norway.
Got it.
Element two is the real-time digital twin, the mirror image that you see in your headset. It moves when the real thing moves. It shows the real-time data. That's what we already know.
And the third piece?
The third piece is the kicker. It's the AI-driven predictive model.
So it's not just showing you what the robot is doing now, it's telling you what the robot is going to do next, or what might happen to it.
Exactly. It links the past, the present, and the future into a single view. And you experience all three of those layers simultaneously through spatial computing. Yeah. That's the phygital world. It's not one or the other. It's a seamless continuum.
So just to make this concrete, I could be wearing a Visionaire, I look at a machine, and I see its current operating status, but I also see a sort of ghost image of it breaking down in 2 hours if I don't go and replace a specific filter.
Precisely. The predictive AI model visualizes that future state based on current data and historical trends. It's telling you, attention is needed here before it becomes a crisis.
But to do that, I mean, to have a headset show me the future of a robot arm in real time, the amount of data and the speed at which it has to travel must be insane.
It has to be virtually instantaneous. And that's why we have to talk about infrastructure. It's the boring but absolutely critical stuff that makes all this possible. We all have 5G now. It's great. It gives you a latency of around 10 to 50 milliseconds.
Which feels instant when you're just browsing the web.
It does. But for the industrial metaverse, the paper's already looking beyond that to 6G.
And what are the numbers for 6G? What's the goal?
We're aiming for 0.1 to 1 millisecond of latency, sub-millisecond.
Okay, my brain can't even process that. Why do we need it to be that fast? Can a human even perceive a 10 millisecond delay? My own reaction time is nowhere near that good.
You might not consciously perceive it with your eyes, no. But you absolutely 100% perceive it with your sense of touch, with haptics.
Touch.
Yes, your visual system can tolerate a little bit of lag. Your brain is amazing at smoothing it over. If a video stutters for a frame, you notice, but your brain fills in the gap. But if you reach out to touch a virtual control panel, or you're performing telesurgery, and you feel the resistance 50 milliseconds after you see your hand make contact,
the illusion breaks.
The illusion shatters. Your brain rejects it completely. It feels mushy, it feels wrong, it feels fake. For this internet of senses they talk about, where we can actually feel and manipulate things online, that sub-millisecond speed is non-negotiable.
And it's not just about speed, it's about location precision too.
Yes, exactly. 6G positioning precision is targeted for 0.1 to 1 meter. In a factory, you need to know exactly where that worker is standing relative to the dangerous moving machinery, not roughly in that area, exactly where their feet are.
And this brings up another buzzword we hear all the time, edge computing. Why can't we just do all this processing in the cloud? I mean, the cloud is infinite, right? It has all the processing power we could ever need.
The cloud is incredibly powerful, but it has one fatal flaw in this context: the laws of physics. The speed of light is, unfortunately, too slow.
Wow. Okay. It's not often we run into the speed of light as a practical limitation in our daily lives.
It is here. Think about it. If you send sensor data from a factory in Germany to a massive Amazon or Microsoft server in Virginia to be processed, and then send the result back to Germany, that round trip takes time, even at light speed through fiber optic cables.
And if a robot is about to drop a multi-ton crate on someone,
you can't wait for Virginia to tell you to stop. The decision has to be made locally. You need the processing to happen at the edge, which means literally on the device itself, or on a small server in the same room.
So the brain has to be in the room.
The brain has to be in the room. For safety and for speed. I like to think of it as the difference between a reflex like pulling your hand away from a hot stove and a conscious thought. The edge is the reflex. The cloud is the conscious thought you have afterwards, analyzing what just happened.
That is a fantastic analogy. So let's take this reflex speed, hyperlocal technology and go into the factory. Segment 3. The source calls this the industrial metaverse.
And it's so crucial to distinguish this from the consumer metaverse we heard so much about a few years ago.
Right, this isn't about buying digital sneakers for your avatar or going to a virtual party.
No, this is a shared, persistent virtual space for serious work, for 3D modeling, for quality inspection, for running production operations, for training. It's a work tool.
And there's a huge sustainability angle here, which I honestly didn't expect to be so prominent.
It's massive. If you can prototype a new car entirely in a virtual space, you don't have to build a multi-million-dollar physical clay model. You don't waste all that material and energy.
Or reconfiguring an assembly line.
That's an even better example. If you want to test a new layout, you can reconfigure the line in VR. You can move the virtual machines around, run simulations, see where the bottlenecks are. It costs nothing. The alternative is shutting down the entire plant for a week and physically moving tons of heavy machinery, only to find out it doesn't work well. The waste reduction is enormous.
Okay, let's get into the specific case studies from the paper, because some of these are just wild. Case study 1, WELD-E, that's WELD-E, robotic welding.
This one is fascinating because it's the perfect blend of XR, AI, and robotics.
So the scenario is a human expert, a master welder, who is guiding a robot welder remotely.
Right. Welding is a highly skilled job, but it's also dangerous. It's hot, the fumes are toxic. You don't want people breathing those fumes day in and day out if you can avoid it. WELD-E allows the expert to be in a clean, safe office wearing a HoloLens.
And in the HoloLens, they see a digital twin of the weld site.
A perfect real-time copy. And they just talk to the robot.
Just with their voice.
With their voice. The system uses a model like OpenAI's Whisper for speech recognition. And the source makes a point of mentioning that it's been fine-tuned for languages like Greek, which shows the level of specificity and inclusivity they're aiming for.
But here's the part that really blew my mind. The WELM, the Welding Large Language Model.
Yes, this is a key innovation. This is the safety layer.
It doesn't just translate what I say, it rationalizes it. Can you explain that?
This is the safety net. Imagine you're the welder. You're tired at the end of a long shift. You look at the pipe and you say, okay, weld that joint at 5,000 degrees, but you meant to say 500. It was a slip of the tongue.
A simple mistake.
A standard translator would just pass that command along. Weld at 5,000 degrees, the robot would obey, and you'd melt the part, or cause an explosion or a fire.
Right. The robot just does what it's told. It has no common sense.
But the WELM does. It analyzes the command in the context of the situation. It knows physics. It knows metallurgy. It knows that 5,000 degrees is an irrational and dangerous temperature for this specific metal under these conditions. So it intercepts the command.
And what does it do? Does it just refuse?
It either corrects it automatically or asks for confirmation. It'll say back to the operator, confirmation required. 5,000 degrees is outside safety parameters. Did you mean 500 degrees?
It's a spell checker for industrial physics.
That is a perfect way to put it. It prevents the simple slip of the tongue from becoming a catastrophe. And it's all paired with computer vision. Specifically, they mentioned fine-tuned YOLA-NAS models to visually identify the parts so the robot can see, listen, and think.
That is incredible. It transforms the robot from just a dumb tool into a true partner. Okay, let's move on. Case study 2, waste sorting.
A slightly less glamorous job.
Not glamorous at all, but absolutely essential and incredibly dangerous.
Extremely. We're talking about construction and demolition waste. It's a mess of wood, concrete, metal, but it's also full of nails, broken glass, sharp objects. Hand sorting that stuff is a recipe for injury. Tetanus shots are a standard job requirement.
So how does the digital world help here?
It's about human-robot collaboration. They use the term cobots.
Cobots.
Collaborative robots. They're designed to work safely alongside humans on the same conveyor belt. The dynamic is really interesting. The humans handle the complex decisions. Is that a piece of recyclable plastic or is it a contaminant? Humans are great at that kind of ambiguous classification. Robots are terrible at it.
But the robots are good at the heavy lifting.
Exactly. The robots handle the heavy lifting and the repetitive picking, while the human acts as the supervisor and quality control. But the tech gives the human superpowers.
Superpowers, like X-ray vision.
Literally. They use X-ray cameras positioned over the conveyor belt to detect things like nails or metal rebar hidden inside a block of wood. The human operator, wearing an XR headset, looks at a piece of wood, and the headset overlays data on top of it saying, warning, metal inside.
And haptics come into play here too, the sense of touch.
Yes, the source mentions providing tactile cues. So when you, as the operator, classify an object with a gesture, or if the system detects an error, your glove or controller might vibrate. It's creating this closed sensory loop between the human, the sensors, and the cobot.
So you could reach for a piece of wood and your hand buzzes to warn you that there's a nail you can't see.
Exactly. It beats sticking your hand in a pile of jagged metal and just hoping for the best.
No kidding. Okay, case study 3 takes us to the Aalto factory of the future in Finland. This one feels like a video game UI brought to life. The follow-the-line repair scenario.
We've all been there, right? Trying to find a specific room or a specific machine in a massive, unfamiliar building. Now imagine a cluttered, noisy factory floor. A critical machine breaks down. You're the technician. You have no idea where pump 43B is located.
Normally you'd be fumbling with a paper map or trying to zoom in on a PDF on a tablet.
And you'd walk in circles for 20 minutes. You spend more time finding the problem than fixing it. Here, they use UWB ultra-wideband positioning. It's like GPS, but it's accurate to within centimeters, and it works perfectly indoors.
And what's the user experience like for the technician?
It's brilliant. You put on a HoloLens too. A bright green, glowing line appears on the actual floor in front of you, projected in your vision. You just follow the line.
Like in a video game.
Exactly like a video game objective marker. It guides you around forklifts, it routes you around known hazards, and it takes you directly to the broken machine. No maps, no searching, no asking for directions.
Just follow the green brick road.
And the best part is, once you get there, the headset's camera recognizes the machine and automatically pops up the correct repair manual and the live data stats floating in the air right over the physical object.
That is pure efficiency. It cuts out all the figuring out where I am and what I'm looking at time.
Which, in a crisis when a production line is down, is everything. Time is money, and this saves a huge amount of time.
Okay, let's shift gears, literally. Segment 4. The automotive revolution. The source dives into a project called MetaBrake.
This is a project led by Brembo SPA. If you're into cars, you know them for their high-performance brakes.
The bright red calipers you see on sports cars.
Those are the ones. They're developing a next-generation electrified braking system for connected cars. But the innovation here isn't just the brake itself. It's how they're building it. It's the meta factory.
Explain that concept, the meta factory.
Before they built the physical factory to manufacture these new brakes, they built the entire factory, down to the last nut and bolt in the metaverse.
Every single workstation, every robot.
Every workstation, every robot arm, every conveyor belt, every parts bin. A complete one-to-one digital twin of the entire facility.
Why would they do that?
For a few key reasons. First, to test the assembly line layout and optimize the flow, to run simulations and calculate production costs with incredible accuracy. But most importantly, and I love this detail, for ergonomics.
The human factor. It keeps coming back to that.
It's central to this whole revolution. They created digital avatars of their workers and had them perform their tasks in the virtual factory. They could see, oh, if we put the wrench on that shelf, the worker has to twist their back in an awkward way 500 times a day. That's a repetitive stress injury waiting to happen.
So they can fix the station design before they ever buy a single physical desk or tool rack.
That's amazing, isn't it? Usually you build the line, people start getting hurt, and then you have to spend millions of dollars retrofitting it. This way, they design the safety and comfort in from day one.
And it wasn't just for them, was it? They brought other people into this meta factory.
Right. They invited their suppliers into the metaverse. So instead of emailing 2D blueprints back and forth for weeks, the engineer from the supplier can put on a headset, step into the virtual factory, walk up to the assembly line and say, hey, that part you designed doesn't quite fit with our sub-assembly. Let's adjust it. They can solve problems in real time, collaboratively, inside the simulation.
That's real collaborative innovation. It's not just a buzzword here. It's practical.
It creates a feedback loop that can save months of development time. It turns a slow, linear process into a fast, parallel one.
Okay, we've been very industrial so far. Metal, waste, factories, brakes. But the AIoTI paper takes this fascinating detour into culture and heritage, segment 5.
It does. This is where we see the softer, more artistic side of spatial computing.
Let's start with holographic concerts.
This is the dream of the global jam session finally becoming a reality.
So the scenario they lay out is pretty ambitious. You have a drummer in a studio in Tokyo, a singer in London, and a dancer in New York.
All performing together, live, on a shared virtual main floor.
Now, we've seen virtual concerts before in video games like Fortnite. Is this just that?
No, this is a whole different ballgame. In Fortnite, Those are pre-recorded animations of an artist's avatar. This is live motion capture. The actual performers are being tracked by an array of pose-tracking cameras in their respective studios in real time. Their full body movement is digitized and projected as a photorealistic hologram onto this shared virtual stage.
And what's the experience for the audience?
You wear a VR headset.
Hmm?
You can choose to sit in the virtual audience and watch it like a normal concert. Or, and this is the really cool part, you can actually teleport onto the stage and stand right next to the holograms. You can walk around the drummer while they're playing a solo. You can see the singer's technique up close from any angle.
But again, we have to talk about latency, the physics of the internet. If the drummer in Tokyo is even 50 milliseconds off from the singer in London, the whole thing sounds like shoes banging around in a dryer.
It sounds absolutely terrible. The music completely falls apart. This is why the source emphasizes two critical technologies: network bonding and a global clock.
A global clock, what is that?
It's an incredibly precise synchronization mechanism. The network has to ensure that the drumbeat from Tokyo arrives in the ears of the audience in London and New York at the exact precise moment relative to the vocals and the other instruments. It effectively has to delay the faster signals by a few milliseconds so everything hits your ear at the exact same time.
It's a technological tightrope walk.
It is. It pushes the global internet to its absolute limit. It requires incredibly stable, high bandwidth, low latency connections.
From the cutting edge of music to the preservation of the past, the second case study in this segment is Stangerholmen.
A beautiful, historic trading site in Norway, established back in 1884. A collection of old wooden buildings.
And what's the primary threat to a site like this?
The elements, mainly. Climate change. You have humidity, temperature fluctuations causing the wood to rot and degrade. And of course, there's always the risk of fire or theft.
So how does an IoT-based digital twin help save a collection of old buildings?
It's about giving the site a nervous system. They install an array of discrete sensors everywhere, monitoring temperature, humidity, structural integrity, vibration. If a big storm hits, the digital twin shows the conservators, who might be hundreds of miles away, exactly which part of which building is experiencing a dangerous spike in humidity.
So they can see the damage happening on the screen before it would ever become visible to the naked eye.
Exactly. They can intervene before the rot sets in. And on the security side, they talk about intrusion detection radars.
Radars, not just cameras.
Right. Radars that can detect unauthorized people or even animals approaching the artifacts, even in complete darkness or bad weather. So if a raccoon or a thief tries to get into one of the buildings at 2 a.m.
the digital twin lights up like a Christmas tree
and sends an instant alert to the security team. It allows a small remote team to protect a priceless, sprawling historical site. It's what they call phygital preservation.
I love that. Using the most modern technology imaginable to save the oldest parts of our history.
It's a really beautiful application of the tech. It proves this isn't just about corporate efficiency, it's also about cultural stewardship.
Let's move to our next segment, segment 6, energy and urban planning. We touched on wind turbines with the immersive triplet, but the training aspect here from Siemens Gamesa is crucial.
Wind turbines are modern marvels, but they are huge, they are expensive, and they are terrifyingly high up. You do not want to be training a rookie technician on a real one, 300 feet in the air over a churning sea.
No, probably not. That sounds like a recipe for a multi-million-dollar disaster, or worse.
So they use VR training with headsets like the HTC Vive.
What's the specific detail that makes this training so effective? It's not just watching a video, right?
Not at all. It's the physicality of it. The trainees have to physically kneel down. They have to walk around. It's a room-scale simulation. They have to actually duck under virtual pipes and reach into virtual cabinets to grab tools.
And the haptics play a role.
A big one. If they try to walk into a virtual wall or a piece of machinery, their controller vibrates intensely. It trains their muscle memory and their spatial awareness of the cramped environment. They learn to operate a complex telescopic crane inside the nacelle, that's the head of the turbine, without any risk of causing a real multi-million-dollar accident.
It's failure without consequence.
Exactly, which is the best possible way to learn a dangerous job. You want them to crash the virtual crane 100 times in the simulation so they never, ever crash the real one.
And rounding out this segment, urban planning, virtual architectural design.
This is about giving city planners the ability to see and experience the city of the future before they pour a single yard of concrete.
The capability is visualizing things like new green spaces or changes in traffic flow.
Right. Planners can put on a headset and walk through a proposed park, but more than that, They can run powerful simulations. If we build this park here, how does it measurably change the air quality in the surrounding neighborhood? If we change this road to be one way, how does the noise pollution shift?
But the source mentioned something I found really strange and fascinating here. Haptics in cities.
Yes, tactile interactions with city models.
What on earth does that mean, feeling the city?
It's a bit abstract, but it implies things like feeling the texture of proposed building materials on a virtual model. Or, and this is the more interesting idea, receiving haptic feedback that represents data. Imagine running your hand over a virtual 3D map of the city and feeling a buzz or a vibration in your glove that gets stronger where traffic congestion is highest.
Oh, that's actually really cool. So you could physically feel the bottlenecks in the city's infrastructure.
It turns abstract data into a physical sensation. It makes the problem tangible. It helps planners grasp the issue pun fully intended.
We've covered a lot of optimism, a lot of incredible innovation, faster chips, safer factories, holographic concerts. But segment 7 is where we have to pump the brakes a little. The horizontal issues, the dark side of all this.
We have to. Because when you connect the physical world to the digital world this tightly, the risks become physical too.
Let's start with telerepair risks. We talked about the expert welder controlling a robot remotely.
Or a surgeon in London operating on a patient in New York using a robotic arm.
What happens if the Wi-Fi drops?
Or even worse, what if the connection doesn't drop, but malicious data is injected into the stream?
You mean someone hacking the robot arm?
Precisely. In the old days, a cyber attack meant stolen data. It was bad. Someone stole your credit card number or your company's secrets. In the digital world, a cyber attack could mean a multi-ton robotic arm swinging wildly and hitting a human worker. Or a welding robot being told to overheat a pressurized pipe until it explodes.
The robot itself becomes a weapon. That is a terrifying thought. Physical harm from a single digital line of code.
They call it a kinetic cyber attack. And it leads directly to the next problem, the question of responsibility, the who do we sue question.
Right. If the network lags for just a split second.
If the network lags and the remotely operated robot drops a load of bricks on a car, who is legally responsible? Is it the operator who was controlling it from 1,000 miles away? Is it the network provider who promised low latency? Is it the software company that built the interface? Or the robot manufacturer?
The lawyers are going to have an absolute field day with the metaverse.
It's a massive legal and ethical gray zone that has not been solved yet. It's going to take years and years of litigation to figure out where the liability sits in that chain.
Then there are the ethics of the AI itself. The paper brings up the DeCapo project, which is an AI assistant for the circular economy.
Right. It's an AI designed to guide workers on how to best sort and recycle materials. But we have to be really pragmatic about the risk of bias in these systems.
How can a manufacturing AI be biased? It's just dealing with machines and materials.
It all depends on the data it was trained on. If the AI learns from historical data that contains human errors or outdated, inefficient practices, it will learn and then enforce those errors.
Yeah.
Or worse, if the training data reflects historical biases in a workforce.
What do you mean?
Well, for example, if it learned from past data that task A is usually and most efficiently done by people of a certain height or physical build, it might not assign that task efficiently to a perfectly capable worker who doesn't fit that historical profile. The AI's advice could inadvertently discriminate.
So you could end up with an AI boss that is subtly or not so subtly biased, leading to inefficiency and unfairness.
Exactly. It can create operational bottlenecks and a toxic work environment, all based on the limitations of its initial training data.
And then there's privacy, with a capital P, specifically eye tracking.
This is the big one for workers and unions. These headsets, especially the high-end ones, track your eye movements with incredible precision. That's how they work, how you select things. But that means the company now has a data log of exactly what you were looking at all day long.
And for how long you were looking at it.
For how long? Why did John stare out the window for a total of 4 minutes and 12 seconds at 10 a.m.? Why was Sarah looking at the safety poster instead of the conveyor belt? It creates the potential for a level of surveillance that is incredibly invasive. Companies are going to have to be extremely transparent and careful about how they use and anonymize this data, or workers will simply revolt.
And finally, under risks, is standardization. The boring but absolutely essential silos problem.
Imagine if you bought a new toaster, but it only worked with bread baked by the same company that made the toaster.
That would be incredibly annoying. I would return it immediately.
That's the danger we face with the industrial metaverse right now. A metaverse platform built by Siemens needs to be able to talk to a robot built by KUKA, which needs to be visible in a headset made by Apple. If they don't all speak the same digital language, if they don't use open standards like USD for 3D assets or OPC UA for machine communication, it doesn't work.
The phygital world breaks apart into a bunch of walled gardens that can't talk to each other.
Absolutely. Open standards are the only way this thing scales beyond individual company projects. It's a foundational requirement.
Okay, let's try and synthesize all of this. We've been on quite a journey.
We have, yes.
We started with a piece of high-end consumer hardware, the Apple Vision Pro 2. We talked about the M5 chip, the Vision Air strategy, and then we just fell down this massive rabbit hole into the industrial, real, digital, virtual continuum.
Into the phygital world.
We saw robots that listen to Greek and correct human error, factories built in the cloud to save workers' backs, and sensors that protect 19th century trading posts from the weather.
It's a massive, sprawling landscape of innovation.
What is the one thing from our deep dive today? What should it be?
For me, it's that the metaverse isn't dead. It just put on a hard hat and got a job.
I love that. That's perfect.
It went to work.
Yeah.
This whole wave of technology is not about escaping reality anymore. It's about augmenting our shared reality to make it safer, more efficient, and more sustainable. It's about circularity, reducing waste by testing everything virtually first. It's about extending human expertise and capability across any distance. It's a tool, not a toy.
That is a really powerful reframing. It's not a video game. It's a power drill for the 21st century.
A very, very smart power drill.
Exactly. Now, before we sign off, I have one final provocative thought for you and for our listeners to chew on.
Okay, let's hear it.
The AIoT source material deep inside dropped this tiny little crumb that has really stuck with me, the concept of the Internet of Senses, or IoTS.
Yes, it's on the far horizon, but it's there.
The paper explicitly mentions the goal of incorporating smell and taste into these immersive experiences.
It does. It's the final frontier of digital immersion.
We've basically mastered sight and sound. We're well on our way to mastering touch with advanced haptics, but are you ready for a future where your remote repair session includes the actual smell of the factory floor?
Or, more importantly, the smell of a specific circuit board that's starting to overheat.
Exactly.
Yeah.
If you're the expert in London guiding the rookie technician in Tokyo, maybe smelling the distinct scent of ozone or burning oil is the critical diagnostic clue you need to prevent a fire.
It adds an entire layer of sensory data that we completely ignore in our digital world right now. But it also sounds incredibly intense.
Are you ready to taste the phygital world?
I think I'll stick to the headset and the haptic gloves for now.
Fair enough. But the future is coming, and apparently it smells a little like ozone. Thank you so much for diving deep with us today.
It was a pleasure, as always.
We'll see you all in the phygital continuum. Stay curious.